Okay, so here's yet another example from class 16, and I don't know if I've gone too far with this because I've already made some really long videos for class 16, but maybe more is better. I think I started this problem in fall 21 yesterday, so I should probably finish it. That's my thought process here. So this is actually adapted from a problem from Beer Johnston. It's problem 823. So this is a mechanics materials book, right? So you can see some. Maybe I could say, hey, this is stuff people will learn in mechanics materials, but forget about it. We want to find. We have the solid shaft AB, so it's this guy right here in between there, and it rotates at 600 RPM and transmits 80 kilowatts from this motor, right? So that the power is the same all the way through, right? So, but this shaft is rotating at 600 RPM. That's the shaft we care about, and it's connected to gear F right here. So this is like the output right here. So the out right here. So we got power in and power out, and this is the intermediate shaft, and we want to do an analysis on it. And so I said the shaft diameter is 60 millimeters, right, which is pretty damn big, considering that this gear right here is 60 millimeters radius. So it's 120. Yeah, so like the shaft is like 1/2 the gear size. That's pretty. That's a pretty large shaft compared to that gear. But anyway, continuing on, and the material, the yield strength is 120, and we want to find the safety factors. And I think I even tried to do some kind of crazy thing in mine where I put I drove a pin through it, right? So I said that there's a 60 millimeter hole drilled through the thing. So the gears are secured with a pin. Now that doesn't really make a lot of sense, to tell you the truth, but we're just gonna go with it. But you need like a hub on the gear in order to get it to stay, and then put the pin in there, and the arrangement would be kind of crazy, and it doesn't make a lot of sense to use a pin. It's actually a terrible thing. But I wanted to stress concentration. That was kind of weird, right? So let's take a look at it. First thing I want to do, because I have RPM and power, I want to look up in chapter 3 and find my relationship, and these are kilowatts and RPM. So I'm going to use this equation right here, which gives us torque if we have power, H. Of course, those are in watts, notably, and the N is an RPM right there. So let's turn those 80 kilowatts into 80,000. So we get torque is going to be equal to 9.55 H over N, or 9.55 80,000 to be watts, divided by 600, and so we get 1,273 Newton meters. And now for the loads onto this thing, I guess all of that was part of the loads too, right? Let's see. Well, looking at this, by the way, I said that this shaft rotates that way, so therefore this gear is putting a force like right there onto this gear. So this is gear C right here. So this is going to be FCY if I choose that as Y, and that is Z, and this is X right there, right? And something we might not know yet about gears, I'm altering this original problem just slightly. Something is that they have to have a pressure angle, right? So this isn't the only force. This is the force that causes torque onto the thing, but there's also another force, a radial force, that has to go along for the ride, and it can't pull it, so it's got to push it, right? You can't pull the teeth. So this is going to be FCZ, and if this is going that way, then the torque must be coming this way, right there, because this is still in static equilibrium. So the sum of the moments about the x-axis right here is going to be that torque minus FCY times the radius of this, which they're telling us is 80 millimeters, right? So I'll just call that, I had this as symbols, so it's the radius of C. So we're going to say that FCY is going to be that torque, 1273 in Newton meters divided by 0.08, because this has to be in meters, right? And so they're going to give us, I'm going to put this into kilonewtons then, right? So this is actually going to turn in, I'm going to divide it by 1,000 in my head. Maybe I'll do it by, divide it by 1,000, right? I'll write it. I haven't been very consistent about that, but I changed the, divide the thing just until I get the kilonewtons. And then if we want FCZ, we multiply this, which is the run, times the tangent to get the rise, right? Because there's an angle right here. There's a pressure angle. And I'm going to say it's a 20-degree pressure angle. Let's assume, I'll go assume pressure angle, which we usually use that symbol for pressure angle right there. So we have like that right there is going to happen. That's the pressure angle that's taking place right there. Phi. I think it's phi. So that's 15.92 times the tangent of 20 degrees, and we get it's 5.793 kilonewtons. And now we need to get the forces that are onto this guy over here. Now, notably, this gear is above this, right? So we need to draw that. I'm going to draw both gears this time. Here's the shaft in between. And I didn't. By the way, I should actually have put in the reaction forces right there. You know, the Rx and the Ry, but doesn't matter right here in terms of what we're trying to accomplish. But here is our FCZ and our FCY. But here, if this is trying to turn it clockwise, this guy better be trying to turn it counterclockwise. That F, and this is going to be DZ, and it also has a pressure angle. We're just going to assume it's the same pressure angle everywhere. And then we'd have like some reactions here, and we don't know what directions they're going to go. And they're actually acting at both bearings, so we don't even want to make a designation. I guess up here. So, and that's not X. That should be Z. That should be Z, right? But we don't know. This is just for show right there, and you don't show a torque because it's not on there, right? The torque is inside the shaft, so it's not exposed, and don't have to write it in there. So here's the sum of the moments about the x-axis right here. So all we really have is this FCY times our RC, and then we're going to have our FDZ times our RD. So we need our FDZ is really just going to be our that force 15.92, and it's going to be times we could actually just go with millimeters, right, because they're going to cancel each other out. So that's going to be 60 right there, right? So we expect a larger number for a smaller gear right in here, and we're left with 21.23 kilonewtons. And then if we need the FDY, that's just going to be our 21.23 times the tangent of 20. So we end up with 7.726 kilonewtons. And then we do our standard thing with our shear moment diagrams here. So I guess I'll try to make it a little neat. But through repetition, we should be pretty good at these, at least soon. I don't think I'll be able to draw them exactly the same, but similar. Right. And the loads that we want to have, okay, so this is my Y and X. Here's going to be my Z and X. And the loads that are placed on here, let's see, this one is coming upwards. So that's going to be our up at 15.92 kilonewtons. And over here, this is going to be the downwards one of this guy right there. And he is our 7.726 kilonewtons. And then looking from the top, we're going to see that we have this guy coming right here, and he should be our 5.793 kilonewtons. And lastly, this one's going in the positive direction, so he's going to be this guy right there. Let's see, drum in the center, something like that. Didn't do a great job of mine. And he is the 21.23 kilonewtons. And the distances, we should probably put those on there, are 120, 160, and 120. All right, so we have a little symmetry action going on here. 120, 160, 120, 120. That should be a 20. 160 and 120. And I don't want to take up too much space here. I get everybody, yeah. No, that wasn't very good. Look at that. That's kind of sad. I don't know. I'm wasting my time doing this problem, but that's fine. Let's see the reactions. This is a teeter-totter one. All right. Sometimes I think I'm predicting this guy's got to be down. See, he's our R, and labeling. This is the A, and this is Y. They did a weird thing where they went A, C, D, B. I like to go in alphabetical, but it's okay. So this guy, I think he's going to be up, but he's going to be R, B, Y. This one's kind of hard to say which way he's going to go. I actually know the answer to this. This is the teeter-totter dilemma right here. So I know the answer, but you have to be careful with this guy. He's actually going this way, even though that's going up. It's the sheer amount of force here makes this one have to go up. So this is the RAZ. This one definitely has to go up, right? So he's RBZ. And so we do the sum of the moments about A, and that's going to give us 1592. I'm going to keep it as kilonewtons and millimeters because they're just going to cancel each other out. I'm just going to get kilonewtons as my answer. So that's our 120, and then minus 7.726, and 120 and 160 is 280. And I'm getting over onto this side. I'm not using the paper very well. And then this one is also positive, so R, B, Y. And so we're going to add another 120 to that. Does that, and so is that 400? I think that's 400, yeah. And so we're going to get an RBY equal to, it's actually very, very small. So this one had a little bit of a chance of actually going in the other direction, but it's very small, 0.6322 kilonewtons. And then the sum of the forces in the y direction equals 0. I didn't put an arrow Oop, come on. Oh, I'm already. Is it already 15 minutes long? Wow, time flies. Jeez. All right. So we have negative RAY and a positive 15.92 and a negative 7.726 and a positive 0.6322 equals 0. So RAY is equal to 8.826 kilonewtons. All right, so if we were going to do the shear moment diagram, we would say we have a negative 8.826, and then we're going to go up 15, which is going to give us a positive 7.094, right? But we're going to come downwards with a 7.726. We're going to get a little tiny little thing, which we can expect to be equal to a negative 0.6322, because this is coming back up, bringing it back to 0. And what we find here is a negative, so it's going to go downwards. So we multiply 8.826 by 120, and we end up with 1,059. Now these are going to be, this is the moment in Newton meters, but this is kilonewtons multiplied by millimeters, so we end up with Newton meters, right? So the kilo kills the milli. Then we take that 7.094 and we multiply it by this, and then we add it to this. Or we could do the other thing, is we could take 120, and we're going to see that this has to be positive up here because this is a negative area, so it's got to bring it back down. So we're going to see that this is going to be 0.6322 times 120, and I think I get 75.86. That's what it looks like on my page, 75.86. Let me double check with my values right here. So I got 0.6322 times 120, 75.86. Yep, okay. So you can see that we actually cross over from on this one right here. This one, let's see, I'm running out of room here, but some of the moments about A is 0. I'll do the next line down, just write small, and we get 5.793 times 120, and then we're going to have a negative 21.23 times our 280, and then so this time is going to be a plus RBZ times 400 equals 0. RBZ is 13.12 kilonewtons. Sum of the forces in the Z direction equals 0, downwards right there. And we have RAZ is actually negative RAZ because of the direction that we're showing here. This is my guess, kind of guessed knowledgeably because I have it written down. Right? And then negative 5.793, and then but a positive 21.23, and then a negative R. Well, no, I got this. I have that answer. Right? I just got it, 13.12. So we got RAZ. We come up with a 2.314 kilonewtons. And it's positive because I did recognize that this is actually going that direction right here. All right, so we want to get the, oh, I didn't do this part. This is going to go this direction, and it's going to be actually negative because Z is actually down. So 314 kilonewton, and this is the moment, so he's in Newton meters right there. He's going to go an additional one upwards of 5793, so this ends up being negative 8.107, and then it's going to come down at 21, so that's kind of a substantial little one right there, and that becomes 13.12, which is supposed to be the same thing as that right there. So looking at this, we kind of come up at a not so steep angle, then we come up at a steeper angle, and then we're going to come back down. Right? So I didn't leave myself a lot of room right here. But at this point right here, we end up getting a negative 277.7, and this one, I'll make a liter. We got 1574 Newton meters. So if we want to get the maximum moment onto here, we take a look at the moment at, and remember this is called C, and this is D, C and D. So at C, it's the square root of 1059 squared plus 277.7 squared, right? They're both at C. Important distinction. And I get 1095 Newton meters. And then the moment at D, and I get 75.86, so it's not going to hardly matter at all because this one's so much larger. And so we get, 1,574, right? Didn't even matter. That one didn't even change the end value at all, probably just fixed. Now, these are the loads. Now, I might want to go to geometry next because we have a really weird one. This is a weird stress concentration, and I picked it because it was weird. Where we have, this is going to be table A1510, right? So we have, we've drilled a hole into this. Now we actually might even be considered trying to use something where there was like a pin inside the thing, but let's just do it with a hole, right? Let's not worry about that. The pin is putting a force onto the thing. So we have a torque and we have a moment, right? So the bending. But look at the nominal is a very strange thing. It's also has the diameter of the little hole is also part of this nominal stress. If we look up here for the torsion, we have J over C, right? It's kind of weird, right? They're calling it C, but we want to use this with TR over J, right? So it's actually the J and R. So this is like really J divided by R, but I don't know why they call it C. They also notice that there's two different locations, A and B. We're going to go ahead and use B because we're going to combine it with the bending. But I think they're trying to say that A is actually where the largest stress is going to be. These are interesting and different scenarios. Right? You might have looked at the other stress concentrations and said, bah, I'll just use the thing I want to. But no, you need to use for the nominal stress, you need to use the thing that this was all based on. So what we're going to do first is we're going to get the geometry, right? So the little d, the hole, I said, was 6 millimeters, right, in the original. So it's a 60 millimeter shaft and a 6 millimeter hole. So that's going to be 6 over 60. I could do that in my head, 0.1. So from that, 0.1, we're going to use for here, 0.1 is almost 2.2. In fact, I decided it was 2.2. Even though it's actually a little bit above 2.2. Look at that. Isn't that? Yeah, you could make a case. 2.22, maybe. I don't know. This is 2.24. I mean, this is 2.4. So 2.3. I mean, yeah, that's actually, I don't know. But I've already used 2.2 in my equations, in my solution. So don't Don't judge me too harshly. And then for this one, I said I used 2.9. Once again, I could probably be a little higher because this right here is 3 right there, right? Because we're 2.8. For whatever reason, we skipped 3 and went to 3.2. But right here, so let's go ahead and pick KT for bending is 2.2 and KTS for shear is 2.9. I know I flipped them. All right. So we're pretend these stress concentrations, even though this is a ductile material. All right. So that's another thing that we're making as part of this. So we have the max bending is going to be. Oh man, I think this pencil needs new lead. I have all my spare leads for this size lead at home. Okay, one too small. Let's see. Sitting right by my end table, next to my Barca lounger. All right, so KT. I guess I decided to write it this way. It's going to be KT times the nominal stress, and the nominal stress is this guy right here. Right? So I'll write that equation out. M over pi d cubed divided by 32 minus d squared divided by 6. That's a weird one, right? So 2.2, and I got from up here. Moment is, I'm running out of lead, 1574 divided by, and this is pi 0.06, 60 millimeters divided by 3. I mean, not 3, raised to 3. And then minus, and here is our 0.006, our 0.06 squared divided by 6. And I get a maximum equal to 196.9 megapascals. And then I can go for my tau max. Now this is not absolute maximum shear. This is just the shear max. I'm calling it max because it's not abs max, right? We still have to do that later. So don't be tempted to do this. But this is going to be okay. So looking at that equation from here. This is J over C. So we're going to take torque and divide it by this value right here. I don't know why they decided to make it so weird. But so it looks very similar to the thing up above. Pi d cubed over 16. I get that right? Yeah. And then minus d squared, yes, divided by 6. So we're going to get our 2.9, and the torque from way back in the beginning was 1,273. 1,273 divided by pi 0.06 cubed over 16 now, minus 0.006 times 0.06 squared divided by 6. So much detail. Tau max. All right, so that's going to be 95.12 megapascals. And I went ahead on my page. I guess I'll just summarize the thing. Well, this is both tension and compression, but I'll just always draw it as tension when we have this type of situation right here. And so this is 196.9 megapascals and 95.12 megapascals. So there's our stress state. We can find our tau abs max because this is uniaxial, and we can use that more straightforward equation, which is actually, if you want to find it, it's this equation right here. This will be the radius of a Mohr circle, and like you can even see it's right there, right? So we can use this more straightforward equation, more straightforward. See why that's funny? It's more. It's sort of like a pun. It's not really a pun. So that's what is the square root of this 196.9 divided by 2 squared plus my 95.12 squared, and I end up with 136.9 megapascals. And then if I have the von Mises now, that's going to be, I won't write down the equation again, right? It's just that squared plus 3 times 95.12 squared. Take the square root of that. And I get 256.7 megapascals. And the yield strength was told to us, that is not very good grammar, of 120. So the maximum shear stress theory safety factor is SY divided by 2 divided by tau abs max, or 120 divided by 2 divided by 136.9, and it's not looking good for the home team, 0.44. I'm not going to go more than 2 decimal places on my safety factors. And then the distortion energy theory, therefore, is the yield strength divided by the von Mises, 256.7. We can see that's not good, 0.47. So I say redesign. And do I have my redesign thing? I could probably put it up in there. My little design little table here. I didn't do it. I guess I didn't. Okay. Do I have my recent ones? Where are the recent ones? No. Okay. Well, let me open it up in a. Let's see. I had. I think it's in assignments. I think I had it actually under 8. It's the 20th. Yeah, I did that today. So there you go. Here you go. So this is another example right here. So I could go like copy this, make a copy of it, and go to example. Let's see, F21. Boy, I got a lot of stuff in here. Where is F21? There you go. Put it right there. So boom. And so this is example 3. And maybe I get rid of this. And I said, and this is in metric, so that's nice. And so this was 120, the shaft diameter. Well, this is going to be a little wrong. Yeah, 0.08. No, 0.06. Yeah, it's going to be slightly wrong. And so I get the torque of 1273. And the maximum moment was 1574. And the stress concentrations that I said I was going to have was for bending was 2.2, and for torque was 2.9. You can see I got pretty small numbers right there, but I don't have the correct numbers because my nominal stresses are different. Right, my nominal stresses, I'd have to adjust for those. And I think I actually might have, yeah, I did this problem right here. Here's the problem where I did it in Excel. And I actually have 3 instead of 2.9 there for some reason. But you can see that I did all the way down there to the bottom. Here's your 0.44 and your 0.47. So if we wanted to redesign it, well, for one thing, we have to be careful here because of the stress concentrations were based on the stress concentrations were based on the proportions of the hole. So are we going to make the hole up the size? So it's got to be an iterative type of process right here. But what I would typically do here is, instead of changing all of this, maybe All right, so this is my own benefit right here. I would say, let me do my copy it here and take this diameter right here, and I'm going to do a goal seek and maybe set my design for the redesign part of this. Maybe I want 1.5 as my safety factor, or in this case, sort of design factor. So I go to data and then up to what if goal seek, and I want to set all the way down here at the bottom, a lot of stuff, a lot of information. I'm going to set my maximum shear stress theory to 1.5 by changing, so I hit that button right there and change this. So I'm going to change the diameter, and boom, it says I need an 88.98 90 millimeter shaft. So a 90 millimeter shaft. Oops, for whatever reason, I guess I hit the cancel button instead of the OK button. So let me do that again. Maximum shear stress theory, set that safety factor to 1.5 by changing this value right here. And then I hit OK, and I got 88.98, and you can see that the von Mises is actually 1.6 right there. But you know, the stress concentration isn't exactly right, because now you'll note that my and I didn't actually write it out anywhere. Where I should have wrote the D over D calculation somewhere in here, right? So I could even stick that in there if I wanted to go like D over D right here. So right here, it's going to be this. No, it's going to be that divided by that. Boom, here's our 0.1, right? It's like we don't really need extra sig figs, but let's do this one instead. Now we have 0.067, and you can see that the stress concentration actually goes upwards, right? So we might want to change the diameter of the hole, maybe. But this whole thing is kind of messed up because of the size of the shaft compared to the gear. This is a gear that's 120 millimeters diameter right here, whereas the shaft is now going to be 90 millimeters, right? That's not much gear left, right? That's only like, you know, to each side, right? There's only like 15 millimeters to each side, right? Of the thing that so like there's some redesigning that needs to take place of this whole thing. But anyway, it isn't. We if we want to get correct onto this, we want to make sure we're using the correct safety. This right here. So we might want to take 0.09, right? But we're gonna for the hole here. Actually, look at that. No, there you go. 0.009. Boom. Now that would be correct. Now these stress concentrations are correct, but we don't have the 1.5 that we needed before. So just be aware that when you're doing the design, sometimes you have to like make a guess and then do like an iteration if you want to get to the exact right thing. So there you go. 38 minutes. Is anyone going to watch this video? I don't know. Maybe. It's another example, but I didn't make an FEA of this one. Would have been interesting, maybe. It's a little what-if thing, because you can't really put a pin right there where the gear is. It needs to be just to the side of the gear, because you need a hub. And you really don't want to put a pin in as a means to transmit torque. It's just not a very good idea.